Hi everyone. So good evening. We'll wait for a few minutes. Let others join if anyone is going to join. Yeah, hello Ankush. बढ़िया भाई. सर और भैया भैया भाई. हाँ भाई, मैं आईआईटी कानपुर से हूँ. Just we'll start in a few. Yeah, good evening, Soumya. We'll start in a few minutes. I mean, I'm just waiting if anyone else is going to join. Okay, so I feel people will join. I mean, just let me. Okay, so let's start with today's class. So, first of all, good evening to everyone who's present. I mean, there are only two people, and greetings of the day to everyone who will watch this on YouTube. So, I'm Swastik Sharma. I am a TA for the course Smart Grids Basics to Advanced Technologies, being taken by Professor NP Padhy and Professor Premlata Jena. Oh, thank you. And I am a TA for this course. I am Swastik and I am a PhD student at IIT Kanpur. Uh, so thank you, Ankur. But I mean, everyone teaches at their own way. So you should attend a few classes and then make your mind regarding what everyone is doing, how everyone is teaching, right? It's not fair to judge people in just two classes. So take your time, give them time, and see if they are going, if you feel the lectures are good enough for you. Okay, so last time we ended with distribution automation. There we discussed a few aspects, right? What's right now happening in distribution system? What is SCADA? What are smart metering, and how the grid is monitoring the distribution system entities, right? So now we'll dive deeper into the structural elements of the distribution automation. So over there, the most you'll see is SCADA. That SCADA is called, just a second. Yeah, SCADA is called supervisory. Just, okay, supervisory control and data acquisition, right? Its task is to provide you with control mechanisms to control the entities at the distribution side. Entities, by entities I mean IEDs, your switch, your circuit breakers, and other stuff. And its job is to acquire data. So power systems work on data, right? Without data, you won't be able to judge what is the state of the power system, right? The health of the power system, you can judge it by looking at the frequency, voltage, and current, right? So without data, you won't use red pen. Okay, I'll use red pen. Just a second. I think this is fine. Let me increase it. Okay, so I hope this is still visible. Supervisory control and data acquisition, right? So yeah, without data you won't be able to judge what is the state of the system, right? So that's what is there in SCADA. So SCADA consists of servers. So these servers are real-time servers, historical data servers, and application server, right? So what these servers do, they store data. A real-time server, as the name suggests, they store real-time what are the values of V and I, right? V and I at the particular location you are interested. In the next minutes, just bear with me, and I'll show you a SCADA diagram as well, where you will be able to, see how this data is necessary, or how this data really comes into, how, why acquiring this data is necessary, right? And why storing historical data is also necessary. And also you can unmute yourself at any given point of time, just to, and let me know if I'm going fast or slow, right? Yesterday's sorry, I shouldn't say yesterday's, last week's class was a bit long, 2.5 hours, so nobody wants to sit with me for 2.5 hours. So I'll try to be, I'll try to increase my pace, but yeah, let me know if it's too much for you. So you need real time. What is the data at real time? The V and I values, historically, how the V and I's have shaped, and you have an application server. Application server is nothing but, like for example, if I want to see, right, I want to visualize what is happening uh, in my distribution system. This application sets a framework for that, and then you have workstations where all of this data is viewed, right, by the operators. And on the and on the and on the other aspects, so SCADA needs to communicate this data, right? And for this, it sets up field from the field devices, it sets up a communication servers. So these communication servers, since you want the data to be relayed from remote locations, like for example, if your data is at you're sitting at Delhi and you want to visualize what's happening in uh, I should talk about a particular distribution system, right? So let's say I'm sitting here at IIT Kanpur. I'm at my lab, and I want to visualize what is happening at some bus which is very far from me right now, right? So for that, what we need to do is we need to set up communication channels. So we discussed communication channels last week as well. So these communication systems and channels are required for it to relay this data to the server, right? And from there, operators look at this data and take real-time decisions if they have to. So yesterday, Mayur, I don't know if he is present today. So he asked a few valid questions. So I will also discuss them, but just bear with me for some time, right? So, as I suggested, SCADA needs to be in communication with the real remote terminal units. So these remote terminal units contain the input output, contain uh, ports for input output. They have we need data collection. We need to process that data. I mean, what you get what could contain false information, so you want to remove those false information or outliers, and you want to translate that data so that it's easier for the human who is sitting over there looking at the data to understand what is really happening with the system, right? So that's what RTU's job is, to have an input output port, collect the data, process the data, and translate the data and relate to the master station. The master station is the place where you are sitting right now and looking at the data, right? So to summarize, master station is the place where you remotely control everything, right? For your all of your control algorithms, whatever you want to do, you sit at some place and you do it. Then you have RTUs, which relay the data from field devices to you, and then you have communication systems which help you in communicating this data from field devices to the master station, right? Now, a SCADA, a basic block diagram of SCADA is something like this. Yeah. So SCADA is something like this. So you have a master station where you want to issue commands, right? So you want to do supervisory control. What I mean by supervisory control is you want to, let's say, trip or close some uh, relay circuit breaker. Then you want to raise or lower your OLTCs. Let's say you have OLTCs, right? On load tap changers. So you want to raise or lower their taps. You want to open or close some sectionalizer or switches. You want to start or stop something, right? And you have to set some set point values at certain location, right? So your everything works with regards to a reference value, right? So if you want to change set points, just a second. Yeah, am I audible? My internet disconnected a bit. So can someone just let me know if I'm audible? Yes, okay. So Yeah, so that's what, so that is the job of the supervisory control that you want to provide to the distribution system, right? You want to provide your IEDs that are there, which will take the signal and do whatever you want to do while you're sitting at your master station. These are then sent to this remote terminal unit, which contain analog output or control output ports. So you can have either analog output or digital output. So let's say digital. When I say digital, your relay only deals with on or off, right? So if you want to do on or off, it's a digital output which gives a signal 1 0. Analog output is like if you have to give some kind of a reference signal or an analog signal, such as let's say you want to provide that, okay, this set point value needs to be of this much quantity, this much frequency, right? So for that, you need the signal to be analog. And you take in values as well to relay it to the supervisory control and data acquisition unit, which relays it to the master station. So for that, you have analog input and digital input pins. You also have pulse accumulator. The job of the pulse accumulator is nothing but to you know set a point at which you are sending this data, right? Over there, we were discussing about PMUs and SCADAs and RTUs, right? So PMUs, what they do is they sample your signals and they send it to you by controlling the resolution of the data. When I say resolution, you want to send, let's say, if I want to do transient analysis of my system, right? What I mean by transient is how my uh, voltages or currents are changing in sub-seconds. So when I say sub-second, it's like milliseconds or microseconds. For that, I need to do time dynamic or transient analysis, and over there, PMUs are better suited because their resolution is quite high. So IIT Kanpur has developed a PMU for distribution system. It's called a micro PMU, and this PMU can sample data 100 times in 1 second. So what does that mean is it can sample one data in 10 milliseconds. So that's quite high, right? So you can get a clear picture of what is happening dynamically in the system. But SCADAs don't have that functionality, right? So they can send values in 1 to 2 seconds. So they are a bit slow. The resolution suffers over there. So that's why the SCADA is now being replaced by not just SCADA. It's the SCADA. SCADA is like it's you'll. I know I don't know why I'm talking about it right now, but this will be discussed in week 4. But still, I want to tell you that resolution in SCADA is quite slow. So that's why PMUs are getting pushed for your pushed for enhanced operations at the distribution side. So RTUs they send all the data that they are required. They send statuses of the relays, alarms, any alarms that have triggered, sequence of events, analog data, accumulator data, and diagnostic results. Let's say you're sitting someplace and you want to diagnose what has happened over there, right? Why the signalizer closed? So it can send you diagnostic results as well. So this is the whole system of SCADA and how it operates with respect to the RTU, right? So the RTUs basically they are nothing but microprocessors, right? So a microprocessor does nothing. It simply whatever you ask it to do with respect to your analog or digital input output signals, it manipulates the data and sends it to you. So it's like a microprocessor that is used to transmit and provide data to the SCADA system. Just give me a second. सुरेश मेरी क्लास है तो मैं तो लूंगा तुम बैठ सकते हो so that is the function of SCADA, right? Now let's move forward. So we discussed, and this should come. So let me show you how a SCADA snapshot looks like. So I took the liberty of getting the SCADA screenshot of our whole IIT Kanpur power supply network. So can anyone tell me what kind of distribution system is this? What kind of configuration this distribution system has? Anyone? Yeah. Can you tell anyone? No one? So I'm audible, right? I just miss it. I think I'm audible. Yeah. So what kind of distribution system is this? So is it only radial or is it loop or is it meshed? That's what I'm talking about.
Mesh.
Yes, it's a meshed, yeah, it's a mesh system, but it has circuit breakers in between. So as you can see, this is a sorry. So this is a circuit breaker. This is a circuit breaker. These are all circuit breakers. So their usage is to change the topology of your distribution network, right? Let's say one of your feeder untimely that its supply got something happened and its supply is removed, right? So having these circuit breakers, what it does is you can extend your feeder so that it can supply the other distribution system in contact. Sorry, other another feeder in contact with it, right? So it's kind of like a meshed, but it's connected with respect to circuit breaker. So as you can see, all of the lines, all of the circuit breakers and everything you can see over there, right? All circuit breakers, all transformers. So it's just a snapshot. I can't give you detailed view regarding this. So that's not something that that I can give you. But yeah, I can't show you how it works. It's not really in my control, but I got this for you from somewhere. So you can see you can see your transformers, you can see your circuit breakers, your lines, if they are energized or not, right? So that is what is the function of SCADA. I sitting at my smart grid control center over here where the SCADA is. So I can sit over there and I can just see if what is happening to the IIT Kanpur distribution system in real time, right? So that is the whole idea of having SCADA. So we discussed smart metering, right? So I think this is just going to be a brief review. So we discussed last week what was smart metering. So conventionally, what used to happen, you could have automatic meter reader, or you had someone come into your home and keep a record of whatever you were consuming, right? That's called manual reading. And all of this data was through a human or manually communicated to a where it was processed and sent to a database where all of the suppliers, the energy suppliers or the DNOs, distribution network operators, they could process and send you bills to your home, right? So whatever amount of energy you're consuming, you could be charged for that. But in smart metering, that's not what happens. So you add what? You add communication system in it. So now you have a neighborhood area network or a wide area network, which is connected to a gateway. And this gateway is connected to your meter data management system that is connected to database. And your energy supplier needs only be in contact with this gateway, right? It does not need to be in contact with each smart meter individually. It does not have to be I mean that data, he does not want to know, only the gateway is contact, which is getting information through communication systems from your smart meters. So that's the whole difference between smart meter and conventional meter. And you the this what does this do? So earlier the data used to be provided monthly, right? So you had either monthly data being sent to the DNO, but now DNO can access this data in real time. In real time, it can know what is happening at the distribution system using smart meters. So that is what is uh, exciting about this, so that it's all about real time analysis. So he does not need to be, the DNO does not should not have to wait for a month to know what has happened to your supply, how much consumption has increased or anything. It gets everything in real time. So, so this was India. So, so how does smart meter processes data? So first of all, it needs to, acquire the signals. So what kind of signals does it need to acquire? Let's say that I'll talk about, let's say it wants to measure how much voltage or current you are. I won't talk in terms of power. Let's say voltage or current that is coming to your feeder at which your smart meter is connected, right? So it acquires this VI data. Now this VI data can have aliases. So when I say aliasing, it could mean that certain uh, uh, inaccuracy has kicked in due to the fact that the sampling rate was less than your fundamental component of your signal. When I say fundamental component, so our voltage and current operate at a frequency of 50 hertz, right? So this is the fundamental component of the signal that there needs to be. So it operates at 50 hertz, but let's say I somehow only acquire the data at 12 hertz. If I acquire data at 12 hertz, what will happen is my signal would become very distorted. So let's say I'll draw it. That would be much better. So let's say this is one signal that I want to acquire, right? Its frequency of operation is 50 hertz. And I acquire data only here, then here, and let's say then here, right? So what I'm getting, I will be getting something like this, that my signal is this, right? So this is not how my signal is supposed to behave. This signal is, it should be, you should sample it more than what it's supposed to be, its fundamental frequency is supposed to be, right? So if you do that, if we sample it at a much larger pace, let's say 26 hertz, or let's say 30 hertz. If I do that, let's say I sample it here, then again here, 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 and here. So now the quality of my signal would be something like this. So, so this means that the conditioning is directly dependent on how quickly you sample your signals, right? If you want to do a steady state analysis, you can go for a low sampling. But if you want to do real time analysis in which you are sampling, you want to do transient or dynamic analysis as well, you need to sample at a higher level. So the so the fundamental thing that it does is that the frequency of input signal should be less than or equal to twice, right? Or I should not say twice, I should say Nyquist frequency. So Nyquist frequency is that the sampling rate of the ADC, or let's say if my sampling rate is Fs by 2. So this Fs by 2 quantity should always be greater than or equal to the frequency of your input signal. And this would ensure that aliasing is not there in your signals, right? So this is what happens in signal conditioning. It removes aliasing. Or let's say your signal is now aliased, right? It has some low frequency component. So what you should do, you could pass it through a low pass filter, and if it has a very high frequency component, you should pass it through a high pass filter, right? Sorry, if it has a high frequency, you should pass it from a low pass filter, and it has a low frequency, you should pass it from a high pass filter, right? That is what the signal conditioning does. And then you need to convert it. The analog signal cannot be sent, it needs to be converted to a digital signal. So that is what the ADC block does. It converts the analog signal to digital signal. Then you do all the computation you want to do, and then you communicate the signal to your database management here, right? And these are your derived measurements, right? So you want to allow only your fundamental component, not all of, or not in any way a high frequency or a low frequency component that could have creeped in your signal by poorly conditioning it, right? So that is the whole process of the distribution system automation, your SCADAs, your smart meterings. We'll discuss about PMUs, but it's for a later time. We'll discuss it in week 4, right? So any doubts up until now? We'll start a new thing. Any doubts? Does anyone have any doubts? No doubts? Okay. Okay, you guys know everything. So let's move forward. So the next topic at hand is distributed energy resources, right? So when I say what are distributed energy resources, can anyone tell me what are distributed energy resources? So you must have gone through the lectures, right? Lectures of this week on NPTEL. So always remember, sir, these classes or these doubt clearing classes are not a substitute of the lectures that are being provided by the instructors, right? This is just a short doubt clearing, and not short, it's 2 hours long, so I shouldn't say short, but it's kind of like a doubt clearing or a problem solving session. So right now there are not many problems because we are not dealing with anything maths over here, but yeah, I mean,
Example, renewable energy resources.
Yeah, I mean, yeah, renewable energy
You
systems can
said
be a subpart of DRs,
wind
but
turbine.
yeah, yeah. So, but DRs are small power resources that can be aggregated to power a large or regular load, right? So we should say, I'll use red pen. Someone asked me to use red pen. So, small power sources can be aggregated to power regular demand. So I used many words, right? Many keywords in this definition. So I said small power sources, then I said aggregated, then I said the regular demand. What do I mean by these, right? So these are small. So these are small enough that they cannot alone I mean, if it's the singular, right? One DR. So these are small enough that they cannot power your regular demand. I mean, let's say you have solar photovoltaic at your rooftop, but that cannot power your whole demand of your household, right? So these are small power systems that can be aggregated. When I say aggregated, let's say your neighbor has, you have, sometimes let's say your other neighbor, he has gone for a vacation for 4 or 5 months, right? His power is, it's not being used in his house in its entirety, right? So it can be aggregated to power a regular demand, let's say your household only. So these are very small power, not very small, but these are small power resources that can be aggregated to power a regular demand. So I used this figure. I mean, this is from your NPTEL lecture only, but that's not these are not the only available DRs. There are more DRs in picture as well. Your EVs are also DR. You can, I mean, right now they cannot discharge, but yeah, in future people are, working on discharging EVs as well so that it can power your house or a building, right? V2X they call. So, right. So, I mean, those can also be DER. So DERs are small power resources that can aggregate to power a regular demand. So that's the gist of it. I mean, so these are not bulk electric system, right? Right? Let's say thermal power plant. That's very bulk. That's called a bulk power system. So it's not like that. It's these are just small power systems, right? So in the residential sectors, so these DRs include solar photovoltaic that you have on your rooftop, or let's say you have a farm. Natural gas fired fuel cells, so you could have hydrogen fuel cells or gas fired fuel cells, which are used to, create electricity through electrolysis, and these can also be uh, used. And you have emergency backup generators. So someone said renewable energy resources, right? So not entirely. I mean, if you have a DG set at your home, right? You have seen there are DG sets. I mean, the building, the Department of Electrical Building at IIT Kanpur, it also has a DG set, right? It can help to empower this. Then you can have small wind turbines, right? So the research is going on. So there are small, very small wind turbines that can be used to power your load as well. So at the residential sectors, these are a few things. Not the end of it. There can be many. You can think of them. At the commercial sector, they can also include solar photovoltaic, but in large number. Your fuel cells, your combined heat and power systems, CHP we call, biomass combustion, hydropower, and wind turbine. So, this biomass power plant, if you see IIT Kanpur recently, there are hamlets of villages in somewhere far from IIT Kanpur, not very far, but they are far enough. So over there, they didn't have electricity 4 years back, right? So IIT Kanpur, what they did over there, they set up a microgrid using biomass based power plant. Why biomass? Because over there, villagers, they have cows, so they have access to cow dung. They get leaves, this whatever there is, the dry waste from your agricultural facility. So they use it and throw it to that combustion zone where biomass is created to to uh, power the load at their in their village. So right, so biomass can also serve, let's say, as a potential DER, right? Let's come to solar energy capacity, right? So this is how the curve looks for installed solar energy capacity for a few of the nations worldwide, and the total installed capacity in this world, right? So this is in log scale. So Don't say, log scale, because if I would have kept it in from 0 to 100, it wouldn't have looked that good. So you see, right, Russia has recently started, uh, getting into the whole idea of having solar energy. If you see world, we have 1418.97 gigawatts of installed solar energy capacity, right? And out of which, how much is India? 73.11. That, sorry, I should say 73.11. And why is that? We are only around 5%, right? This is 5%? 5. So, yeah, we are around 5%. Yeah. So it's very less. And you see our counterparts, Russia, it's like 609.92. And I remember I took this course last year as well. So I went through the slides when I changed them a bit. So last time this was 300 and something, right? So you see, China has in a year uh, mm, increased the installed solar energy capacity by 2 times. And for India, we have just increased it by 13 gigawatts. So you see how far we are lacking, right? And yeah, miles to go we before we even catch up uh, China. You see, they have taken this huge jump over here. But for India, it's a slow jump, but it's still, it's still happening. So let's say where we'll be in, next 5 years. So this is the global irradiation map for India. So as you can see, so so as you expect, your planes to constitute most of the irradiation for you, right? So the higher the irradiation, the if what I mean by irradiation is, so for per meter square of area, how much solar energy can be generated, right? So there, it's in kilowatt hour per meter square, right? It's in kilowatt hour per meter square, right? So you see, Gujarat and Rajasthan, right? They possess very high solar radiation, and you have Ladakh as well, and you have some places in south, right, where there are no plateaus, and you can install solar. So you see, we have irradiation in India, but the adoption of solar energy has been a bit slow. I mean, it is going to increase for sure, but we still have a lot of irradiation that is still being left out there, which is not being used for creating solar energy, right? So let's talk about solar energy system. So what are solar energy system? What is solar energy system? It's the system in which we can convert solar energy to electricity so that it's useful for us, right? So for that, we have a PV cell. So we use a PV cell. So what exactly is a PV cell? So what happens is okay, I'll show it over here, right? I'll come to that. So we have a PV cell, right? And it is used to generate, it can generate zero point 0.5 to zero point 0.6 volts. You know, per PV cell, we can get zero point 0.5 to zero point 0.6 volt, right? So it's very small. We can't, zero point 0.5 to zero point 0.6 is not something that we want, right? So what we do is we arrange them in a module. So when many PV cells form in a given what you say structure, it's called a module. And when we have multiple of modules, we call it a panel. And when we have multiple panels, we call it an array. So that is what is the whole terminology behind PV cell, module, array, and a panel, right? So how does it work? So the from the solar, what we have is we get solar energy, which is irradiation energy. We convert this energy by striking it on the PV cell, right? So what happens is this causes the electrons. Sorry, uh, yeah. So this causes the electrons to be formed into. Uh, sorry. So what happens is when it falls onto the PV cell, it creates electron and hole pairs, right? You all know what is electron hole pairs, right? So denoted by hole, right? So it forms electron hole pairs. So these electron hole pairs, if they have sufficient energy, from the solar energy that we are getting, what they do is um, uh, they start aligning themselves with respect to the PN junction over there, right? So there is this PN junction, diode, right? So when there are certain holes in pairs, so there is this junction. I'll just call it like this. So when there are a lot of these, there is this junction, and when there is sufficient energy in this whole electron pairs, they start jumping this junction, right? So if they get sufficient amount of electrical energy, they start vibrating, and once they start vibrating, they jump this junction, and there is a drift current formation. Electrons start flowing over here, and there is a drift current which starts going in the opposite direction. This is called drift current. So if we energize sufficient electron hole pairs, there will be this drift current which will surpass this potential joint that is formed between the diode, and they jump this and they jump it to form a current, regular current, right? But this current, it's DC, right? So we get a DC output from the solar cells, right? And now we want to be able to use it to power our loads, which are predominantly AC. So we have to first do inversion and conditioning, right? So um, um, they can be feeble, they can be very variable, right? So we need to do conditioning before we can even use it for our usage, right? So we do it. We we use what is called, it's inverter, and this inverter converts DC to AC, and we distribute this energy either for our usage, or we send it to the electric utility for a monetary benefit. Or if we have an energy storage system available at our home, right? Let's say there is this let's say I have installed solar PV array, right? But I know my consumption, right? My consumption increases, has two peaks, one during morning and one late evening, right? So this is the kind of peaks that my load witnesses. One 6 a.m. peak and one 6 p.m. peak, right? Now, when there is abundance of solar energy available, at that time the load is very less, right? So we can't use it to our advantage, right? So what we can do is we can store this in form of in some kind of an energy storage device, and use it at the later time when there is no solar available, right? So this is also possible, and you can store this energy if you don't want to supply it to the electric utility, of course, right? So a solar energy system works in two ways, right? So it works like either grid connected or it works off grid. When I say grid connected, it is connected to a grid, right? So it can supply energy back to the uh, electric utility, right? So that's what is happening over here. You have your modules, you have your inverter, and you have your AC distribution box. So what is AC distribution box? No one knows, right? Someone knows what is an ACDB? So when electricity supply comes to your home, it is not straight away used to empower your loads, right? It goes to a distribution box where there are multiple MCBs, and after that only it is used to supply your loads in your household, right? Why is that? Because you want to protect, let's say if there is sudden, some kind of a fault or something, it should not creep in so that it disturbs your loads, or it creates some kind of an impact to your load. So that's why you use an ACDB, which is then connected to your
It's
meter.
like Liger,
What you're saying?
Liger, stabilizer जो होता है वही।
No, stabilizer is a different thing. So you have a distribution box as well where there are multiple MCBs connected to, so that stabilizer, it just stabilizes voltage, right? And it sends to your home. No, let's say something happened in your house only. So what happened was let's say your one appliance, how should I say, it caught fire, yeah? It overheated itself and it caught
Main board,
fire. Yeah.
main
Yeah,
board, main main
main
board.
board.
Yeah,
Yes,
main board, yes, but we call it ACDB, right? Main board. Okay, yeah. So that
yes.
is
In
the, yeah.
second figure of grid, क्या जैसा ऑफ ग्रिड में है ना, ग्रीन येलो और रेड लाइट, उस टाइप का है।
नहीं, वो I'll come to that. I mean, yes, but will come. I mean, yeah. So this ECDB, since your PVs are now being directly connected across your substation, your where the grid's power supply is coming, so you don't want any fault to creep into that. So that's why you connect it to an ECDB and then you send it to that meter. So in off-grid, how does off-grid function? You have your PV array and you use a battery bank. So when I say off-grid, it's not being connected to the grid at all. So whatever energy it can store in this storage battery bank, it can be used to empower a DC load such as a light, right? An LED light. A charge controller's usage is to, it needs to prevent the batteries overcharge. Let's say your battery is, it's at 100%, it's sitting at 100%, and now it keeps on getting charged and charged and charged. So there is this condition which could result in, decrease in battery health, right? So you don't want that. You want to block any reverse current that can creep in and some kind of an electrical overload. For that, charge controllers are used. So this is an off-grid solution. So personally, I'm not in favor of off-grid solutions. It's because, at least in Kanpur, I've seen, like, many times inside IIT Kanpur only. So it's dusty, right? So right now we are a developing nation, right? It's there's a lot of dust everywhere. So if dust settles in, their efficiency, which is already very low, right? It's between 15 to 25%, right? On a peak day. So you don't want to, you don't, your efficiency goes further down because now there is dust over there. So, and you have to clean it before you can, get that much efficiency back from it. So off-grid solutions, if, like, let's say it's in a perfectly healthy environment where you get rains, frequent rains, and then you have uh, some place. I don't know why my keeps getting. Yeah, I'm audible, right? So I don't know why my internet keeps getting disconnected. Anyway, so this is what an off-grid connection is. So same block diagram I've shown it over here. It's pretty same, right? So you can just check once. It's just the same thing. Now, one thing I want to talk about is how the energy produced from your solar PVs are getting valued for you, right? So there are two kinds of metering infrastructure that are there at present. So one is called gross metering, the other is called net metering. In gross metering, you have two meters. One is a gross meter, and the other is your electricity meter, right? An electricity meter keeps the reading of how much you're consuming from grid, right? And this gross meter, it tracks how much you're sending to the grid, right? So its use is, let's say that the government. So we'll come to that. I mean, so that's how it uses, right? So your solar system, it's being tracked in a different meter, and your energy usage is being tracked in a different meter. But there is one more metering arrangement. It's called net meter. A net meter, so whatever you're supplying and consuming, it subtracts itself from whatever you're consuming, and it presents you only the reading that you are the net of which you are consuming, right? So let's say you developed Y units and you consumed X units, so it keeps track of X minus Y units, right? But in gross meter, let's say you supplied Y units and you consume X units. So the main purpose of this is that the government can give you different money for your consumption, charge you different money for your consumption, and give you different money for your production, right? So let's say I consume at 6 rupees for this X units, and I send electricity at 2 units for these Y units, right? But here I'm consuming at 6x minus Y. So which one is more lucrative? What do you think? Which one is more lucrative from a consumer's end? What do you think is more lucrative? In which one would you feel that that your that your net electricity bill is going to be lower, if I rephrase it well? Hmm? Network unstable. My network is unstable.
Net metering.
Oh, my network is unstable. Is it fine right now?
Yes.
Okay, so what I'm saying is, okay. So what? Yeah, I rejoined. I don't know what happened. So, okay. Mm, I don't know what's happening to my system right now. Okay, let me share my screen again. Sorry for this interruption. I mean, I don't know what's happening. IIT Kanpur's net has been unstable lately. Okay, so I hope my screen is visible now, right? Okay. So so I was discussing the metering arrangement for your solar PV cells, right? Whatever solar PV cells you have. So you have two kinds of metering infrastructure. One is gross metering and the other is net metering. In gross metering, you have two meters. One is called a gross meter, which tracks how much power you're supplying to the grid. Is it fine now? Am I audible? Okay, I don't know what's happening. So I'm really sorry for this interruption. I mean, I really don't want to interrupt, but I don't know what is happening right now. So uh, forgive me. So what I was discussing is there are two kinds of metering infrastructure for your solar PV cells, right? The rooftop solar PV cells. One is called gross metering, the other is called net metering. In gross metering, you have two meters. One meter tracks how much amount of energy your solar PV cells or your solar PV array is producing, and the other tracks how much amount of load your household is consuming, right? In net metering, there is only one meter which calculates the net of what you're producing minus your load, right? So let's say you consume X amount of units and you produce Y amounts of units. So it tracks X minus Y and it charges you only rupees 6, right? At what it wants to uh, procure at the cost of what your consumption of load is. But let's say as a government, I want to give you different amount of money, or I'll charge you differently for the amount of units you produce, and I charge you differently for the amount of units you consume, right? So over there, the thing, let's say I charge you at 6 rupees for consumption and 2 rupees for production. So what my point was, I'm asking, in which case do you think a customer's bill would be less? Would it be less in net metering or would it be less in gross metering?
Gross metering.
Why would it be less in gross metering?
Because
Okay, let's do one
uh,
thing. Let's do one thing. You consumed 100 units and you supplied 50 units. Now tell me what will be this value. X is equal to 100 and Y is equal to 50 for both cases. So what will this value be?
so 500
Yeah. And what will this
gross
value be?
metering and so 300.
300, right? So in which case your bill is less? Net
Yeah.
metering. Net metering, right? So what is happening over here? So in net metering, you are just being charged for the net amount of power you're consuming, right? And you are being charged at the same rate at which you are consuming. Now this creates some kind of a divide in the population. Let's say in distribution system, there are some loads, some households which have PV rooftops, and some households which don't, right? So now take that much amount of money because as a distribution utility, I am paying 6 rupees for the load you are consuming, right? But when I'm getting electricity from you, it is not going to be sold at the same rate. It can be sold at a cheaper rate or at a higher rate, right? So as a utility, I can make losses as well. And for those losses, what I'm going to do, I'm going to increase the bill, right? I'll increase the bill. And let's say there is another household which does not have solar PV. What's the fault of his, right? There's no fault. He never got into this trouble of getting solar PVs. So that is why when the government started subsidizing this, right, subsidizing this solar PV, you can check UP NIDA's website. Each state in India produces its own solar PV guidelines, right? Uh, in any case, you can just go to that state and go to their new and energy development agency, and you can check their solar policies. Especially for UP, I've taken a look. Earlier, they were giving net metering. Now they have switched to gross metering because they wanted to increase the amount of people that could that could get the solar PV panels for their rooftop. Now they have shifted to gross metering because okay, why cross subsidize the households which are not producing, which don't have PV modules, right? So these are the two kind of metering arrangements that you can see if you have a solar PV array, right? Next, we come to a very important thing. So we want to model how does a solar PV cell or solar PV array can be modeled, right? So to model it, we use so in any case, okay, let's model it, right? So as I told you, there is always going to be a diode because why? At the end of the day, at the end of the day, that is where it draws its functionality from, right? It generates electron hole pairs which get charged up. They 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 hop on from the junction barrier and they create drift current, which is also called electricity in your case, right? So what we do is we give them certain amount of lighting current, right? This lighting current comes from the radiation that is happening. Your solar energy is shown as form of a current source, right? So this is a current source, right? So this is IL, as you can see here, right? Which is also called lighting current, the amount of current that the light is producing. Now, a PV cell has its own losses as well. So there can be losses due to manufacturing defects or other things that are present in you know in the PV cells, right? So we do two kind of we use two kind of resistance to model these losses, right? Because at the end of the day, resistances denote how much amount of losses there is in your system, right? So we show losses in the form of shunt resistance. That means it decreases the amount of current that is coming to the end of your nodes, right? So if I use this, so my node will have lesser current. So this comes due to the fact that there can be manufacturing defects. So let's say that some kind of a defect happened during manufacturing. So that is modeled using a shunt resistance. Let's say your design is poor, your cell design is poor, your cell is not behaving as it should, right? So that kind of a loss, because it won't generate the same amount of current that it is promised to, right? So that is shown as kind of a shunt resistance. And for this, if you want no shunt resistance at all, I mean, if you don't want the shunt resistance to be there in the first place, you need to have a perfect design. A perfect design, but still, I mean, there's no such thing as perfect, right? There can always be some kind of defects that can happen. Then there is another kind of a resistance that is modeled for losses. It's called series resistance. So what it does is it creates a voltage drop so that you don't get the same amount of voltage which you expected, right? So this can come due to the contact between different metals. So let's say you're using metal to um, um, place in your silicon this PV cells, right? So some kind of a metal contact can happen. So this metal contacts add to the resistance, right? And let's say that your the top of where you're getting in from the lower end from your which you are connected to your system, it can cause some kind of a loss over there. And your emitter base resistance, it can always, because from there you're getting the drift current, right? So it always is there, and this contributes to the loss in the uh, PV cell, right? So this is how you model it. You model it using a shunt and a series resistance, right? So this is how the working equation would look like if you use a KCL, right? So you get a KCL over here. Okay, I want to get this I. This is ISH and this is I diode. So if I get a KCL over here, it would be, you can get KCL because these three are connected to the same load. So it will be IL minus ID minus ISH, sorry, yeah, and minus I, right, equal to 0. So this is what the condition is over here, right? So your I is nothing but, I'll just do it over here, equal to 0, and your I is IL minus ID minus ISH. So this is what, how you arrive at this equation using KCL. So I have, okay, right? So the diode current can be represented using this. So I won't. So this is not something that I want to get into. I mean, not even the instructors have. So if you want to see how we arrive at this equation, please go and refer to your basic electronic notebooks. That's not at all relevant over here. I mean, we are just showing that this is the diode current, and that's how the current equation will look like, right? And we have a very, so how we arrive at this equation, it's simply, we just do what is called KVL across this loop, and we arrive at this equation too. So now the PV characteristics. So we want to, so for any given diagram, for any kind of a module, its characteristics show how the behavior of the module is supposed to be, right? So let me show you how the behavior looks, right? Earlier I showed you, right, if there is a diode, I'll draw it using blue first. If I energize it using V and I, so its characteristics look something like this. I'll plot it. So its characteristics look something like this, right? There is a knee point at which it starts generating current. So this is I, this is V. Now what I'm saying is I'll connect a current source across it, IL, right? This current source is nothing but the amount of lighting current I'm getting from the solar energy. So now what it does, as from this equation, you can see it shifts it. It shifts the graph below, right? So it shifts it like this. I think, right? So this shift is called IL. It shifts by IL amounts. Now, since this is not what I'm looking for, right? What my, at the end of the day, the I current, I wanted to, this I current, it needs to be, it should not go from this node, it should go into this node, right? So its direction should be like this. Let me draw it. Because now it will generate electricity, right? So what we do is we shift this, invert this graph. So if we invert it, it could be something like this. So this is what this, how this graph is, how we arrive at this graph. So this is IL, right? Or also it's called your short circuit current. I'll come how we arrive at that. So you can see this is how the graph will look like. This I'll just, you see, like this. So this is called your IV characteristics. Now PV characteristics, if I want to drive, how will they look like? P is nothing but V into I, right? P is V into I. So for each V, we multiply I, and oh, more colors over there. Yeah. So for each V, what we do is we multiply and we get some kind of like this. This point, we have the maximum power, right? So the point across, this is called the maximum power point, right? The point at which we get the maximum power from a solar PV cell, it's called MPP, or maximum power point. So you can see the current is called IMP and the voltage is called VMP, and we denote a fill factor, right? So the maximum permissible power that we can get from a PV array or PV cell, whatever you want, whatever characteristics you have plot, divided by the power from its open circuit voltage and short circuit current. So this is called open circuit voltage and this is called short circuit current, right? So this thing is called as fill factor. It is kind of like, it tells you the efficiency of your solar cell. It tells you how efficient your solar cells are, and it's generally between 0.7 to 0.8%. So here, don't think of the efficiency to be like the one that I used, 15 to 25 or whatever, 30%. Now we have increased it, but the current set mark is 25 to 30%, right? So that efficiency corresponds to how much energy from solar we are getting, and how much we are getting as how much solar energy is there, and how much electricity we are producing. That is a different kind of efficiency. That is a conversion factor. Fill factor tells you what is the maximum power we can get from this arrangement and what we are getting, right? So this is called fill factor. It is generally between 0.7 and 0.8. It tells you about the quality and efficiency of the solar cell. Quality, right? Quality is a better term, right? So this is how this is why PV characteristics are very important. Whenever you look at, the manufacturer will give you these quantities. It will give you a data sheet, and from that data sheet you will get you know you will get this PV plot as well. Now the arrangement of these PV cells, they can be either series or parallel. So this graph shows that if there is a single cell, right? So this single cell, this IV characteristic, something like this, right? But if I add one more cell in parallel to it, let's say we have a parallel arrangement of these PV cells, what happens is we increase the amount of current, maximum amount of short circuit current we can get from it, right? And our maximum power point, it also increases. But when we connect it series to series, we see that open circuit voltage has increased, the amount of open circuit voltage we can get, but the MPP, the maximum power point, stays the same. So in series, we don't get the same, we get the same MPP. PV cells have only one electronic device diode. One PV cell, yes. Multiple PV cells, we can have multiple. No, it's not diode. I mean, it's just a representation. So we don't have a diode. It's a different arrangement. But yeah, I mean, in a single cell, we only have that because that is what the uh, open circuit voltage is, 0.5 to zero point 0.6 that we can maximum get from it. Right, and this is how the IV curve will look. If the irradiance it increases, if we have more irradiance per meter square, right, our IV curves, they start increasing. The area between them starts increasing, and if there is more electron density, our short circuit current and everything will increase. So that is why I say that whenever there is a high radiance area, we should have maximum, so we can get maximum solar energy from that place. Right. So this is all related to solar energy system. So any doubt up until now? Any doubt? Okay. I think you've all went through that lecture, right? So you don't have any doubt. So fine. Now let's talk about wind energy conversion systems, right? So we talked about solar energy system. Now let's shift our focus to wind energy systems, right? That are also very that are also a very good source of producing electricity, right? So our solar, it suffers from one thing. What is that? During non-solar hours, when there is no sunlight, we can't get any electricity. We can't extract any electricity from the solar cells, right? So, but wind is available. It is available for us during the day, even at night, right? And more so at night. So, a wind energy system is always beneficial if you want to rapidly deploy or rapidly increase the amount of units you want to get from their renewable energy generation systems, right? So as you can see, this is also a logarithmic plot. The world, I don't have the tabular values, I'm sorry. So world is at a it's at more than 1,000 terawatt hour of electricity wind power generation. But you see, India, it's below 100 terawatt hour. Still, China is leading. China has So it has covered like it is around 1,000 and it is more than 1,000. So it's like very less amount of difference between them. So you see, China, the state, the country is highly dependent on renewable energy resources. So that is what India also wants to achieve, so that its COP26 goals and whatever the goals related to climate goals, they stay on track and they can attain them. Right. So we have A wind farm looks something like this. We can have onshore or offshore wind turbines. So recently I went to, south. I went to Kanyakumari, Rameshwaram and all. And from that stretch, from Kanyakumari to Rameshwaram, you will see a huge amount of wind turbines or wind turbines connected to, and they are huge in number. Huge. I mean, I can't even quantify how many I saw. There were many, both onshore, offshore, right? So these are these are very much required, and they need to be there, right? So say uh, because we have wind energy available. So yeah, I couldn't get the wind energy, the plot where I can say is show you how much potential we have in terms of wind energy. It was available in Wikipedia, but over there the Indian map was distorted, so I didn't get it from there. I repeated the same thing in the last year as well. So I couldn't find. I tried finding them, but I couldn't find a good map. Yeah. So you see, these are wind turbines. So what they do is they can either be onshore or offshore. You see, these are onshore, and this is sorry, this is offshore, and this is onshore, right? So you have uh, these two kind of turbines where why why do we feel that only the coastal areas, can anyone tell me why only coastal areas have this huge potential of wind turbine? You'll see wind turbines everywhere in coastal areas. Why is that? Yeah, someone was
Because
saying.
flow of wind is huge,
Yeah, why is that? Why
high.
is why is wind energy over there? Do
Mm,
you have any idea? I
like
mean,
tidal.
yeah. So
No.
there are few things why it is like this. High speed of wind, right? But why is there a high speed of wind? I'll tell you. So there is a huge temperature gradient, right? So no obstacle. That is also a major thing. But I'll tell you one more reason. There are many reasons, but some of the reasons I'll just mention. One, temperature gradient. So in coastal areas, because there is sea, the temperature is less in sea and more on land. The temperature gradient causes wind to flow from sea to land when it's nighttime, and from land to sea when it's daytime, right? So this causes the that because of this there is a huge potential for wind energy over there. Second, there is no obstacle, there is no plateau, there is no mountain, there are no high rise buildings. It's just coastal line, right? So you can extract maximum amount of energy from over there. Next, there is one more reason, potential reason. It's because area. The most favorable area in India, at least, is coastal areas. You see, there are only roads, right? There are very less amount of, there are, I mean, places um where which are densely populated, but not too much. Coastal areas are generally populated only at certain points, right? Not along the highway or the road, right? So that is why this design is much more suitable over there. So you see, these are huge, around 80 meters tall. So why is that? Because you want to have, because as the height increases, the speed of wind also increases. So you want to get all of the wind energy there is to empower your turbines, right? So this is how a wind turbine look. It has an offshore substation. So whatever you supply it through a substation back to an onshore substation, which is connected to transmission, which is then connected to your homes. So that is how your wind turbines work. So this is out of your nacelle. So this is called nacelle, right? This thing, right? This thing is called nacelle. So you see, we have a hub. We then have a main bearing. This bearing's role is to help it rotate it freely. The wind turbine should rotate freely. They should not experience any kind of a mechanical friction. Just a second. Right, and then you have a main shaft. This is also called a low speed shaft. So it's called a low speed shaft because it's called main as well because it handles all kinds of mechanical stress that is there on your turbines, right? When your turbines rotate, a huge mass of wind falls onto their blade, right? The pitch of the blade is such that the mass of air coming to it attacks it and it starts rotating. So now, because of this mass, this needs to be, something should be there to absorb this high impact of this wind, right? So that comes onto the low speed shaft or the main shaft. It feels the brunt of this uh, movement. Then we have a gearbox. The gearbox design is to increase the speed of the turbine rotation, right? Let's say that your wind blades, they will rotate very slowly. So you have to have a gearbox to increase the speed of the rotation, not the wind turbine itself, wind blades itself, but the rotating shaft. And there is also a brake. So let's say some kind of an emergency and you want to brake it, right? You want to, the conditions are not favorable. It's too gusty right now. So you want to brake the shaft so that it does not rotate. You provide them with the brake. And then there is this high speed shaft, which is directly connected across to this gearbox and is connected to the generator, to which it rotates and generates electricity, right? So now we'll discuss what kinds of you know what kind of wind turbines are there, right? So one is a fixed speed and variable pitch blades, right? So I hope everyone has gone through the lectures. This was very extensively covered. I'll just give a brief review to you because it's very hard for me to touch upon everything. But still, I'll be touching on everything, but just touching them, right? So don't go and say that okay, I did not cover anything, because these are not meant to substitute the original lectures, right? So what we have is we have fixed speed. We want to keep the speed of the turbine rotation at a fixed rate, right? That's what we want to do. So for that, we have variable pitch blades. So how do they function? So let's say the blades rotate. So they are rotating. And it's connected across a wind turbine, right? So this wind turbine, it's nothing but the rotation that it provides. And it is then connected to the gearbox, which is then connected to the synchronous generator. This synchronous generator generates AC power, right? And now you want the frequency to be same, right? So what you do, if let's say the wind speed has increased, if the wind speed increases, the turbine rotation will increase. If the turbine rotation increases, the chances of frequency uh, uh, being affected because of the synchronous generator, it increases, right? So you want to control that speed. So for that, you use a sensor. This sensor sends a signal to the speed control algorithm, which then controls the pitch. Pitch means the attack of wind on the blade. So if my picture is visible, so let's say this is how your blade looks. So you want it to fall on it like this, right? So if it is falling perpendicularly, it'll rotate at a very high speed. But let's say you want the speed is very high, and now you want to decrease the amount of decrease the speed of its rotation. So what you'll do, you'll just tilt it so that not the attack of wind, it decreases. So that's why that is used to control the pitch of the this blades, right? Now let's say you want to have variable frequency operation, right? So let the speed increase or decrease. You don't care. You don't want to control the pitch. So what you can do, you can have variable speed fixed pitch blades. So this is the same thing, but you attach a frequency converter, right? Sorry, I'm saying frequency converter. Signal will go to the gearbox. It won't directly go to the gearbox, but it is
So
used
the
to control.
signal will control the rotation of the gearbox.
No, not the gearbox. It's the attack of blades, right? Let's say I'll just show you. So what is pitch? Let's say I'll do a very good job if I can. So let's say this is how your turbine looks, right? And now wind is falling perpendicularly, right? I don't know how to show perpendicularly. Let's say this. So wind is falling perpendicularly. The attack of the wind is very high, and it will rotate the blade because the wind is falling perpendicularly, right? So the speed has now increased. Now your generator has sensed that, it sends a control signal and it asks to control the pitch. So how do you control the pitch? You rotate the blades like this. So you'll change the blades a bit. So if you can see my camera where I'll show you. So let's say earlier your blades were like this. Now you shift it like this, so that the attack is minimized. Now, not all of the wind falling on it can rotate it, right? So the attack is less. Now the speed will not be that much, right? Where did it go? Okay, right. So that is the usage of this, right? A gearbox can only control
Sir,
certain extent.
sir,
Yeah.
sir,
Mhm.
if the pin, you are saying that the pin of the
Mhm.
fan that will make an angle, that will change its
Yeah,
rotation
the
angle.
nacelle will move in such a way it will not rotation angle. The blades are like this. It will just tilt it a bit so that attack can be controlled, right? Like this, it was like this. It can move like this. Do you see? Your voice, my voice is not coming. Am I not audible? Am I not audible? I'm audible, right? So what it's doing, it's controlling, yeah, it's controlling this movement, lateral movement, right? So if it control this movement, the wind will will not fall perpendicularly. This movement I'm talking about, the
Okay,
nacelle,
okay,
right?
okay.
Right. So, so if you want, let's say the speed to increase or decrease, you don't want to have any kind of a mechanical equipment to control your nacelle, right? So what you can do, you can have a an AC to AC front end converter. Sorry, a frequency converter, right? So what it does is it is an AC to AC converter, which consists of a front end and a back end converter, which is coupled with each other using a DC link, right? So this is front end, this is back end, and this is the DC link. This is also called a back to back converter. Now what you do is you get the AC power from it, and you convert it to DC once. Then you convert the DC back to AC so that it is of 50 hertz frequency, right? And it can then be synchronized to the grid perfectly. So let the wind flow as it wants. You use power electronic converter. These are called power electronic converters to convert the frequency, right? So you are controlling the frequency of operations. But this whole thing, this this device, because it is directly connected across the grid, it is directly connected across the grid, and it's directly connected across the generator as well, right? So the rating of the individual components in this PE converter or this back-to-back converter, the rating is huge, right? So your rating of these power electronic components, it increases. So, and if you know a bit of power electronic components, as your rating increases, your cost will increase. So the cost of getting uh, this back-to-back converter, it increases many folds. This is the way in which you can handle. Or you can have a small scale, for a small scale wind powered domestic system, right? I showed you small wind power turbines. So for that, you can have a rectifier and a voltage regulator, and you can use directly from that voltage regulator. If it is a DC load, you can directly power that DC load, or you can convert it using an inverter to your AC load, right? Over there, because it is a small scale power plant and because it's connected to your domestic system, you won't have the issue of too much wind energy. But if you have, you can always, because it's the size will be smaller, the rating will be smaller, you can control it using this. But for a large scale wind power system, the power electronic converters need, and their rating, it increases many folds, and the cost also increases many folds. But you get the advantage that you can achieve variable speed operation. I'll write it over here. So this is the advantage and cost is your disadvantage, right? And this is how the wind characteristics look like. So there is a cut-in speed below which you can't produce any electricity. And after that, it increases. It is a non-linear relation. I'll talk to you later how to quantify this non-linear relation. And then it attains the rated power at some rated speed. And after that, there is a cutoff speed, after which you shouldn't be producing, if the speed increases more than this cutoff speed, you should not be producing, um, what you say, you should, the system is not allowed to deliver power after it, if after the speed increases more than the cutoff speed. So this is how the wind power characteristics look like. Now, I talked to you about, right? So if you want to achieve variable frequency operations, you can use a power electronic converter which can convert the frequency, right? You with a back-to-back converter. But the only issue is cost. The cost will be high. Now, another kind of research is happening, which is now shifting focus. Let's say you want to achieve asynchronous or a variable speed operation, so you can use DFIG systems. Sorry, a DFIG system is an induction generator, which is called a doubly fed induction generator. So if you remember, I don't know if you remember, but if you remember your electrical machines course, you would have noticed that for an induction machine, their torque speed characteristics, torque speed, right? So it is something like this, right? So this is called subsynchronous operation or motor operation. This is your synchronous speed and this is your generation operation, right? So an induction machine can also act as a generator. That we know. If the speed of the rotor is more than the synchronous speed, it will start producing electricity. That is the whole funda of it, right? So you can have variable speed and you can use a DFIG to create some kind of a system with which you can get uh, even with variable frequencies, fixed voltage, fixed frequency output from your system, right? But as I said, because the rotor needs to rotate at a high synchronous level, right? It's a super synchronous level. How can you make sure that the if let's say the wind speed has fallen, it has fallen down to the subsynchronous level, and now it operates at the it's now starting to look as it's going to operate as a motor, right? So you want to control that aspect. So what you can do is you can use again power electronics components where you connect it across the stator and rotor, right? So when I say stator, oh sorry, when I say stator or rotor, stator is the part where you extract electricity from the generator, and the stator is directly connected across grid. So if I say stator side converter, you just mean that it's grid. It can also be called as grid side converter. So you have again a back-to-back converter where the first AC/DC part is linked to the rotor side converter, and the other DC/AC part is linked to the grid side. Right. Now what happens is, let's say variable speed is there, right? But the pitch is fixed. You don't have to change the pitch. So what do you do? Let's say if the slip is more than what is required to produce electricity at a given frequency, what you do, you supply the remaining electricity back to the grid using this infrastructure, right? Whatever NS minus NR over there, you just take it from the rotor, get that extra amount of energy, supply it using this back to the grid. And let's say now you are at subsynchronous level. Your slip is less than uh, your slip is positive, right? So what you can do, you get the extra amount of energy needed to have the same fixed voltage, fixed frequency operation, power your rotor side, so that the electromagnet or the magnetic field rotation can add to the rotor's synchronous the rotor speed and produce electricity at synchronous level. So this is what's the usage is. You have a grid side converter and a rotor side converter, and by using the bidirectional features of the grid side converter and rotor side converter, you can uh, create a certain kind of a phenomena where you can have a fixed voltage, fixed frequency operation. But there is some, I mean, there are some advantages to it. One advantage we have is that cost will be lesser. Now you'll say, okay, we are again using back-to-back converter. How is the cost going to be less, right? This converter is only used for the fractional amount of power that is needed, right? Around 15, it uses around 15 to 30%. If I could be, so this is what the figure could look like. I think it's 15 to 30%. I don't know. It's 15 to 30%. You can check. I mean, you can let me know if it's wrong, but the rated it is not supposed to be, the components are not supposed to be at the same rated power that is there in your grid, right? So because the rated components rated power is less, your cost will be less. But they suffer from one thing that's called increased reactive energy usage, right? So why is that? Can anyone tell me how do induction machine work? So in induction machine, there are rotor windings which are supplied with three-phase AC currents, which produce rotating magnetic field. Because they are producing rotating magnetic field, they consume reactive energy, right? That is not the case with synchronous generators. Synchronous generators either use permanent magnet synchronous motor, or they have DC field excitation system, right? DC field excitation system does not require any reactive power. So they only come with one downside, which is an increase in reactive energy usage. But still, benefits outpower uh, the disadvantages, and the usage is very much being explored. Now, these are some things that I wanted to tell, but I forgot to tell you about a few things that I think should be talked about. Now, Betts, there is someone named Albert Betts. He gave a law. He said only 59.3% of wind energy can be converted safely to electrical energy. Can anyone tell me, well, like from intuition, why do you think only 60%, close to 60%, 59.3%? Why is that? Can anyone tell me? Can anyone think? Just think. If there is 100% power conversion, what will happen? I just want to see if you can think intuitively, right?
10% in drivetrain,
No, that losses will come, but
10% in
he said theoretically, from the wind energy, only 59.3% wind energy can be converted to electrical energy. Don't think of drivetrain losses or efficiency right now. Just think, why is that? What will happen if we achieve 100% electrical energy from wind energy? So let's say I have a turbine. I don't know if I can do a good job, but I'll draw a turbine. Yeah, very bad. So let's say I'm saying all the 100%, it can convert 100% of energy, all the wind falling onto it. What will happen?
फैन
If
will destroy, फैन
n-
टूट
no, no,
जाएगा
no,
ज्यादा.
no, no, no. I mean, ठीक है, मतलब विंड एनर्जी अभी, मतलब मान लो विंड स्पीड कम है, अगर कम भी है फिर भी हम बस 59.3% ही एक्सट्रैक्ट कर सकते हैं, अगर कम भी है तो. दैट इज व्हाट द लॉ स्टेट्स. I'll tell you, if we get it the efficiency to 100%, what will happen? There will be no wind coming out of this turbine. मतलब टर्बाइन को खत्म होने के बाद विंड रुक जाएगी, पीछे उसके कोई कुछ होगा ही नहीं. ऐसा है? ऐसा हो सकता है? इट्स नॉट पॉसिबल, राइट? विंड कैन नॉट जस्ट स्टॉप. ओके, उसने यहाँ पे दे दिया सारा, अब आगे कुछ नहीं चल रहा. दिस कैन नॉट हैपन. So that is no, that is just intuitively how he came across it. But he thought about it. What will happen if I use 100%? He told, okay, then there will be no wind coming from the turbine, right? After it has touched the turbine, there should be no kinetic energy left in the wind. So what he did was he used computational full fluid dynamics to come up with this law that only 59.3%. It's a very elaborate law. I mean, I have I went through the pain of going through that explanation, how he arrived at that 59.3% value, but it's a whole derivation. I don't want to do it, and I don't even think I can do it without having some reference material with me. So, if you want, you can just check online how he arrived at 59.3. He used some kind of a computational fluid dynamics to achieve at this number, right? But technically, right now, the achievable amount of energy is 30 to 35%. This was given by Betts law, and we have achieved 30 to 35%. And out of this, 10% get exhausted in drivetrain as losses. So, miles to go, right? at least get 45 50% of the energy, right? That's what we're looking at. We're not too ambitious, right? So this is how it uh, this is how what I wanted to, I feel this is all, but let's discuss some um, mathematical formulas and their derivation, right? So I won't go through the pain of giving you the whole derivation. I'm just going to do only that much that is needed. So first of all, the kinetic energy of wind. How can we quantify that? It's half. It's half m.
MV square.
Yeah, it's half
MV
m
square.
mv square, right? And what is the power that we can extract from this kinetic energy?
Yes.
P is equal to what? D by dt.
D by dt.
So we do it. We get what is the expression that we get?
V square dm by
Sir,
dt.
your video is not there, only audio. Can anyone check if my video is also there?
Yes.
Yes. So, Mr. Akhtar, I think my video and audio is working perfectly fine. So there's something with your system. Okay, so you are not visible. I am not visible. I am visible, right? Ankush?
Yes, sir.
Yeah, I'm visible, Mr. Akhtar.
Your voice is coming, sir. You are not visible.
You are visible, sir.
Yes, everyone is saying I'm visible. So I think you should check if there is my somewhere. If I'm there, you just click pin on there and I'll be visible. Yeah. So where was I? Yeah. So power is nothing but d by dt, right? Differentiation of energy with respect to time. So what we get is half v square m dot or dm by dt. Right. What is this dm by dt? Right. How can we have mass and time as a derivative? Right. So don't get afraid. It's nothing but it's called mass flow rate. This is called mass flow rate. Right? This is nothing but mass flow rate. You don't have to think that okay ये क्या बोल दिया भाई, मैं मास को थोड़ी ना, मैं थोड़ी ना, मेरा वेट 8 kg है, मैं 80 kg और मैं टाइम के साथ डिराइव कर सकता हूँ। नहीं नहीं, ऐसा नहीं है. It's mass flow rate. Mass is a different thing. It is quantified differently for wind. I'll tell you how. So the mass flow rate, also called as Q, which is dm by dt, its practical significance comes from the fact that it is rho a dx by dt. Now I'll just give you intuitively how we arrived at, right? This class is very intuitive, right? So let's say this is our turbine blade. This is the attack of wind. When I say attack of wind, don't think that it is not attacking here or here. It is attacking, which I'm just showing a certain area, right? So here wind is attacking. Now the amount of mass or the volume of mass it is picking with itself and depositing at that blade, it is called its mass flow rate with respect to time, right? How much mass it is picking from the air and depositing onto the blade with respect to time. So this is a variable quantity with respect to time. That is why it's called mass flow rate. So we denote it using rho a dx by dt or rho a v, where dx by dt is nothing but velocity of wind, right? So this is what the mass flow rate is. And if we put it back to the wind power, we get power of wind to be half rho a v cube, right? So, so the wind power is with respect to the velocity, it's in terms of cube, right? So it varies cubically. So that is why when I said over here, this is non-linear in nature. This thing, this is non-linear in nature. It is because of the cubic relation between velocity and power, right? But this is theoretically how much we can get. But from Bett's law, power theo is equal to Cp times half rho a v cube, right? Where Cp is nothing but 0.593, whatever, 59.3 it gave. So we can only get 59.3% of,
Actually, I think
yeah, we can get it back from the total wind power that is over there, right? So this is how this comes. So CP, there is in the lecture, Premlata ma'am has given a kind of like a perfect derivation for how you come up with that CP value. I'll ask you to go follow them. I mean that you'll be able to understand them. So I'm not getting into all of that right now, right? So this is what wind energy systems are. So any doubts up until now? Any doubts? So my speed, is it okay if you want me to repeat anything from today's lecture? Just let me know. Otherwise, we'll move on to quiz sample assignment problems, and I just want everyone to be on the same page. That's what my job is. Anyone with questions? Anyone with feedback? Okay. No questions from Ankush, right? No questions?
no, sir.
So just by show of numbers, if someone is, if someone wants to tell me how many of you went through the week 2 lectures?
Sir, I done two lecture,
Oh, 2 lectures. So
but
yeah. So I'll
but
I'll request you, yeah. So what you can do is go through them. I mean, I also went through those 5 lectures, So go through them, come back to this lecture, and then you'll be able to appreciate what we have covered, right? Because I'm covering everything in very small duration, and everything which those 5 videos have covered, I have to cover in 1.5 hour. So it's not possible, and it would seem like you're not getting anything, but that's because the prior knowledge that you should have gotten from those videos is not there. So don't worry if you're not understanding anything, but I'll request you to visit these lectures once you once you see all of those earlier lectures, right? So let's recap what we did today. So we started with SCADA. I talked to you about what is SCADA, what is RTU, why they are relevant. I showed you a block diagram for a, not block diagram, I should say. I showed you SCADA diagram of SCADA snapshot. We say SCADA snapshot of our IIT Kanpur system. I showed you what smart metering is, and then how smart metering and what are the different blocks that it has, what are DERs. So can anyone tell me from the last lecture, if someone has, someone really went through those last lectures, can anyone tell me what is the standard that is used to standardize the interconnection of DRs to the system, to the power system? What is the name?
1547.
Yeah, it's called IEEE 1547. So this is used
47.
to, standardize the interconnection of DRs with the system. Then we talked about the installed solar energy capacity, and you see how 5%, it's just 5%, it's very less. We talked about irradiation, all of the solar PVs, net metering, gross metering. Then we discussed how these IV characteristics, we come up with these IV characteristics. We talked about what is series parallel, and what shape of form series and parallels are better. We talked about wind power generation, and then we ended with the variable frequency operation, where we discussed two kind of um, systems, where one is the synchronous generator with front end to back end converter, and the other is a double fed induction generator, which also uses that, but because it uses only for a 15% to 30% rated power, the cost of the power electronic component is less. Right. Then we talked about some calculation, just to give you a brief overview. What is Betts law? What is the intuitive thing behind Betts law? And that's it. So let's do the assignment. So I think we covered everything in a very short duration. Nice. So let's take our time and let's think. What is in the SCADA system? The front end of processor are interfaced with what? So let me show you the diagram. So this is the diagram, right? Where it is? Yeah. So this is the front end processor, right? And it is coupled with what? You have your real-time data server, you have your historical data server, your application server, and your workstations. These workstations are used to enable human machine interface. You know what is human machine interface? A human sits and watches these machines, and that's why we call it a human machine interface, right? That's Is that a correct explanation? It's just that the human machine interface is like, yes, the humans can, you know, the 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 whole interface between human and machine is provided using these workstations, right? So these are HMIs. So what do you think? What is the correct answer to this first question? Today I'm not going to answer anything. Here you have
D.
to do. Yeah, D. All of the above is the correct answer.
All of the above.
Yes. So what is the function of the data translation application in SCADA? So you have the options: manipulates data before they are presented to the master station. It presents data to the master station. It acquires data from the RTU, or it acquires data from the devices. What do you think is the correct answer?
D.
B is not the correct answer. I'll show you. Right. So you see what data translation does. I did talk about it. So data translation, it makes the data it understandable for humans, right? For a human machine interface, it needs to be able to translate the data into an understandable form so that we be able to manipulate it and tell what is happening with the system, right? So that is what, so let's say this snapshot. So what do you think? Okay, who is creating this snapshot? I did not create it, right? Some kind of a translational tool inside my SCADA system created the snapshot for me so that it is easier for me to understand what is happening with the system, right? So the data translation application, it manipulates the data before they are presented to the master station. That is what its usage is. So the amount of power available in the wind at any instant is proportional to dash of the wind speed. Who can, I just covered,
Cube.
right?
Cube
Yeah,
power.
yeah, it's cube power. Fourth, a PV array has the open circuit voltage 370 volts, a short circuit current 28 amperes, and a maximum power of 8 kilowatt. What is the fill factor? So what is fill factor? It is VMP IMP by VOC ISC. Who can tell me what is the correct answer? You just have to calculate. I'll also do. We have, yeah, I've calculated. So anyone else who has calculated? So the maximum power PMP, what is it? VMP IMP, right? That is what the maximum power is, and it's given to be 8,000 watts. And you know VOC, you know ISC, just put it into this formula, which is 8,000 by 370 into 28. Just do this calculation for me.
8,000 divided by
370 into
370.
28.
0.77.
Yeah, so the correct answer is 0.77, right? Right. What is the most expensive part of a PV system? Think about it before giving the answer. This is a very good question.
PV array.
Right. PV array is the most expensive part of the PV system. So you have
कल
battery
ही एक
storage.
रील देखे थे।
कल कल क्या देखा?
एक रील देखे थे, मतलब वो अपने घर पे लगाया था, बोला टोटल कॉस्ट 98,000 पड़ा है, जिसपे 6 ही पीवी array 6 ही पैनल लगाया था।
So PV array is the
6
most
पैनल 2
expensive
बैटरी।
part of a PV system because silicon, it's expensive. So the percentage of losses in a wind turbine's drivetrain is what? Someone
10
answered
10%।
yes. 10% is the correct answer. So next we have the light generated current in the solar cell depends on what? Short circuit temperature coefficient, cell temperature, cell short circuit current, or all of the above. What is the correct answer? So short circuit temperature coefficient, it tells you that if the temperature, if what is the variation between short circuit current and temperature, right? So if it is higher, so if temperature is higher, so your short circuit current will be more, right? In a sunny day and in summer months, your solar will generate more amount of electricity than in winter months, right? Same goes with cell temperature, and same goes with cell short circuit current. If your short circuit current is more, your I is more, your yeah, so your generated current in the solar cell will be more. So what is the correct answer? I did all of you. I did all of it for you. So you just have to tell me. All of the
all
above,
of the
right?
above.
Yeah. Okay, the blades in the wind turbine work on the principle of what? Pull, lift, drag, or lift and drag. So I didn't cover this.
Pull and
So
drag. Pull
yeah,
and
what?
drag.
Drag.
Drag
Pull and
one.
drag.
Pull and drag. Lift and drag, no, not lift and drag.
Lift and drag. Lift and drag.
Lift and drag, right? Now, which is or are not a part or parts of a remote terminal unit?
D. Historical server.
Yes, a historical server is not a part of your remote terminal unit. Its job is not to have a database or a server where it can store historical data. It just needs to store real time and just push it. So, what is the function of yaw drive in the wind turbine? So, a yaw, this thing is called yaw. Yeah, this thing, I feel, yeah, bed plate. So, can I show you? Mm, I don't think I can show you, but yaw is basically the what is connected to your blades and your. It's not shown over here, but yaw is connected to your blade and your shaft. So what do you think is where did it go? What is the function of that yaw drive? So I have not shown it. I don't know. I should let you answer. Okay.
Turn the rotor according to the wind direction.
So did you look at some kind of Google? Did you go to Google to search for it?
No, sir. I have read the PPT, I think.
Okay,
I
okay.
have.
Yeah, it turns the rotor according to wind direction. Yeah, if you went through the lecture slides, you'll be able to know. So
In
it's
this
fun,
class, also, you have given some. When I was asked
but I
about the
did.
fins of engine.
Yeah, I
Yeah.
didn't call it. I didn't call it that, right? So it's my mistake. That is why I told you that. Who will answer this? Okay, next question. Which of the following components of SCADA consists of a human-machine interface? Where do you think human-machine interface is? A human that interacts with the data.
Communication system.
Communication system? No. Communication system is used to get data from the field devices and communicate it to your RTU. RTU then translates it and then presents it to your master station. Sorry, RTU, I'm saying SCADA, and it presents it to your workstation, right? So the only contact between the human and machine is that workstation, right? Sorry, in that workstation which is present in the master station, right? So the component which has this human machine interface is the master station, not the communication systems, not remote terminal units. So let's see here, right? This is right. So this is your operator workstation, right? That's what I showed you, that provides you the human machine interface, right? So this workstation is present in the master station, which presents a HMI. So next question, which of the following components of SCADA presents data to the master station? Who can give me a correct answer? So we've discussed this several times today, right? I don't know why.
Data translation application.
Data what?
DTA.
DTA.
Data
D-
processing application.
D-
Which one of these? Data processing or data translation?
Translation.
Okay.
Data processing.
Data processing. See, I'll go back to this. Right. So your data translation, what it does is it makes the data into an understandable form, right? But a data processing, what it does is it it processes the data, and both of them can be used to present data to the master station. That is why the diagram has both of them in contact with the master station, right? But a translation data, when it changes into an understandable data, some kind of a noise could creep in, right? That can be taken care, that is being taken care by data processing application as well. So the data, where did it go? So the data, very difficult. Yeah. So the data processing application is the one that presents data to the station. Although data translation application that serves the same purpose, wants to pair with you. What do you want to pair with me? What is this? File pairing. Okay, I don't know. Okay, so the central contact would be always your processing application. So the data processing application. Third question: which of the following is not a disadvantage of solar PV? Okay. Yes. Which of this is not a disadvantage? Yeah, there is no moving.
moving,
Not
no
having
moving
a,
part.
yeah, not having a moving part is not a disadvantage. It is an advantage. Next, which of the following is not cause of a series resistance on solar cell? So we discussed this thoroughly today. So I want someone from you to answer it.
A.
The
Not
B.
foam
causes.
B, sir.
series resistance.
C.
Think
C.
C,
Due
B.
to
B,
manufacture defect.
B, C, A. I need one voice. Someone can use a chat box too. I don't know who is saying what. I have
Not
got
causes. C.
C, B. Naki
C.
Akhtar says B. Okay,
Due to
so the
manufacturing defect.
resistance that creeps in due to the contact between metal contact between metal and silicon, do you think it uh, it causes it causes the current to become less, or does it cause the voltage to become less? Think about it. So the correct answer is C, due to manufacturing. Yeah, my airdrops died. So the correct answer is C, due to manufacturing defects, and I'll tell you why. So we covered this today. See. So your shunt resistance depends on your manufacturing defects, poor cell design, and your poor cell design, right? But your series resistance creeps in because of the fact that your because of the metal contacts with the silicon, your emitter base resistance, or the metal contacts that are there between the uh, switches of your solar PV, right? So the correct answer would be C. So you see, in your assignments, you'll feel that there will be multiple questions where they will use which of the following is correct or which of the following is incorrect. So always read the question twice, right? Just like here we use the word not, and you thought, okay, series resistance में क्या आता है, right? But if it is not a cause of series resistance, that means it is a cause of shunt resistance, right? So the shunt resistance is caused due to the manufacturing defects. Next, which of the following components of a wind energy system supports the weight of the rotor? We discussed this as well. Come on, who can answer?
First.
Nacelle? No. Gearbox? No. So the first,
To wait.
low speed shaft. Over here, I talked to you about it. Here, when this is called a low speed shaft that is in direct contact with your wind blades. When it rotates, the brunt of the mass or the
brunt of the force that that mass exerts on that blade, it comes directly onto the shaft that is in direct contact with the blades, right? So a low speed shaft experiences.
low speed.
Hmm. So the correct answer would be low speed shaft. 8. Which of the following characteristic affect the uh, characteristics of a solar cell? Who can answer this question?
Okay, solar.
C.
See both of
Yes,
these.
both of them can have a direct contact. Next, nacelle does not consist which of the following?
Wind vane. Wind
Yes,
vane.
yes, it does not have wind vane. It has gearbox, it has high speed shaft, it has motor. This is a nacelle. This thing that you see now over here. This is a nacelle, and these are the parts that it has. So, today's class we discussed week 2 intensively. I hope that some of you could get something out of it. If not, I request you to please rewatch the lectures and or rewatch this video when it's available on YouTube. And uh, how temperature affects efficiency of solar cell. Okay. So, Renessa, right?
Sir, we can get short answer questions.
These
Multiple.
questions, these questions,
Mm,
right? So,
yeah, this.
yeah, so when the NPTEL team shared these lectures with you, they shared a Google Sheet, right? Over there, I have this drive folder where you can use it to. Okay.
Okay, sir.
Hmm. Or in each of my videos, I have in description, I have that link of that folder as well. So you can use that link too. Okay, so Renessa, tell me, when I said, okay, I won't use this slide. Why I'm using this slide? I have this, right? So when there is a photovoltaic cell, right? So what happens is the electron energy, sorry, the solar energy, it it impacts the this photovoltaic cell, and it creates electron hole pairs, right? So this comes from the fact that there is some form of energy which is called as light energy or electrical energy, right? But now let's say the temperature is more. There is thermal energy as well. With light, there is thermal energy too. So this thermal energy, along with the fact that there is electricity, this light energy, it impacts them and it imparts this energy in some way that creates more electron hole pairs. So that is why, because the temperature is more in summer days, you will feel that your solar PV cells or your solar PV panels, they are generating more electricity. And in winter days, when there is less temperature, but still there is abundance of sunlight, let's say if you are having a free environment where there is no smog or fog, you will feel that the amount of current that you're getting from your solar PV output is less. It's generally because of the fact that uh, even though there is light energy, there is no thermal energy in it, which can help in creating more electron hole pairs, right? Which aids in creation of electron hole pairs. So I hope you understood, Rinessa, how temperature affects efficiency of solar cell, right? I'm waiting for you. I mean, if you have doubt, energy resistance will increase. Energy resistance, what is energy resistance? What is energy resistance? So when I drew the characteristics, I told you that the amount of short circuit current when it impacts, it directly relates to the kinetic energy resistance will increase. Oh, so you're talking about the energy which is there between the barrier when they have to jump. Mobility also. So you're saying kinetic energy because they're vibrating, so they will feel more resistance when they're jumping, right? So the drift current will be less. That's what your point is? Yes. Okay, so let me tell you one thing. So all of this temperature effects or everything has its limit, right? You can only increase up to a certain extent. Over it, your everything has to, even with increasing voltage, your short circuit current becomes less, right? But it only becomes less after a certain point of time, right? So you can't say that because the kinetic energy increases, the electrons or the hole pairs will vibrate more, and because they are jumping the fence, that potential barrier, they will feel that there is resistance between, because of the increase in this vibration between each electron and hole pair, right? But that is up to a certain extent, after which it causes that effect, not below it. So up until that point, yes, it is proportional to it, but yeah, after it, because mobility decreases, they will feel. But right now, the temperature that the solar energy or the summer days have, they are not, it's not sufficient to cause that much effect on the mobility of electron hole pairs. That is why up until that point, you can say the same for wind turbine as well, right? You just keep on increasing. Why does it saturate? Why the power coming from it saturates? It's because of the fact that there is inherent mechanism which forces it to, convert to a speed, convert to a power which is rated power, after which it won't produce more power because it won't support it. So in actuality, this is not the correct, this is not the only graph that it shows. It increases and then it decreases sharply. If you see online, you'll see this graph as well. So that does not mean with the increase in velocity the power decreases. That is one way of saying that, but up to a certain extent, yeah. Efficiency other than the fixed condition 1000 watt solar A. What did you say? 15 am. Can you unmute yourself? I mean, I don't understand. These are keywords to me. 1.5 am. What is this? Can you unmute yourself? Atmospheric mass. Efficiency other than the fixed condition 1000 watts per meter square. Single solar cell 1.5 atmospheric mass. Here you've gone into a lot of details, but the question says which of the following characteristics affects it. So the effect, it can be positive, it can be negative. Up to a certain extent, temperature affects it. It affects it proportionally. Sorry, air mass, air. I don't know what you're saying. I can't. If you don't unmute yourself, this back and forth will be very, it's very laggy. But yeah, the characteristics are affected with solar irradiance and temperature both up to a certain extent, just like velocity with respect to wind. Any question? Sorry, air mass, sir. I understood. So, for all solar cells available to you, there is a data sheet, right? So, in that data sheet, all of the fixed conditions with which that a particular, IV characteristic is developed, you can see over there, and you'll see that with the temperature increase, you will see that the amount of current, short circuit current you're getting from this solar cell, it will be high. Any
Sir,
Yeah.
in the when it is one air mass, the rays of the sun are overhead, and when it is 1.5 air mass, the sun's rays are vertical to the earth. So,
Mm-hmm.
sir, in the given conditions, which is the irradiance is 1000 watt per meter square, and single solar cell, and 25 degrees Celsius, and in that 1.5 atmospheric mass, the relation with the relation of the temperature with the efficiency is that on increasing the temperature of the solar cell, due to VOC and ISC, which is the short circuit current,
Mm-hmm. Yeah, yeah.
the efficiency will first increase and then decrease.
Yeah.
Other than those conditions which are given,
Mm-hmm.
what will be the relation between the temperature and the efficiency, sir?
Oh, so you're saying other than the fixed conditions, what is the relation between efficiency and okay. Uh,
Because, sir, on increasing the
hmm.
temperature, the short circuit current will slightly decrease, sir, and the open circuit voltage that will increase with the increasing temperature. And because there is a vibrational kinetic energy between the molecules in a solar cell, when the sun's rays will be flowing, because one electron is equal to one proton. So, because the rate of flow of charge is current, so taking all these conditions.
I don't have an answer to that question right now, Renessa. I mean, you've caught me off guard. I've never went to study the efficiency in such a depth because I've never done that. I mean, if you want to do it, you have to look at some kind of a data sheet from for a solar cell. So you have to see that sometimes it's not feasible for me to possess all of this knowledge, right? I don't know. I don't have an answer to that. I'm an electrical engineer. I'm not an electronics engineer. So you have to ask an electronics engineer what is that after if the conditions are removed, what is the efficiency? But but for what the knowledge I possess, for a temperature, there is a there is a coherent relation between ISC and temperature, in which it will increase to a certain extent, after which it won't. And that is what I'm telling you since the question. So for that, I'll either get back to you over email, or you have to wait till next class. I don't have a correct answer to that right now. Anything else?
Okay, thank you so much, sir.
Mhm. So see, you have to think that I also am a student. I don't possess everything. I don't have perfect knowledge of everything. I'm also learning with you. But yeah, I'll get back to you on this as well. Like Mayur asked me a question yesterday. I'll get back to you with this as well. So, any other doubts apart from all of this which we have covered? Any other doubts? If there are none, we'll end this meeting.